Hello there, thank you for joining me again today. On the bench for review and strip down today, we have this rather unique instrument which, to be honest, I've only seen very rarely in the past. And this particular instrument, I know we focus mainly on this channel of radio frequency test instruments such as the Marconi, Hewlett-Packard, Aeroflex and everybody else in between like Rode and Schwartz, but I just thought I'd do a video on this today because it's quite a little interesting unit. I think these were around a lot actually, I seem to recollect, in the 1980s and 90s and up to the early 2000s. I think they've been quite a well-used instrument in many workshops. I think the last time I saw one of these was actually in a TV video repair business. And every technician, I think they had 5 technicians at the time, had one of these on the benches. So it was like a main instrument for them. And we'll see why in a moment, because it's actually packed with some really good features, this particular model. Now, although this is badged up as SJ Electronics Mark II Universal T&M System, Test and Measurement System, this wasn't actually manufactured by SJ Electronics. SJ Electronics is a company in the UK that's still about today even, and that do all kinds of test equipment sales, and so they've just badged it them. But the actual manufacturer of this unit was a company called METEX, and this was known as a METEX Universal Combined Test Instrument Systems and Stations. Now, I think they did different models of this because the reviews that I've read and the information, technical information I've looked at on the internet, shows that the frequency counters on the older models only went up to 250 megahertz, whereas this goes up to 1.3 gigahertz. So it does actually make it quite usable for those wanting to get into or look at radio frequencies into the microwave radio spectrum, certainly at UHF high band at least. So it's actually quite a little gem to look out for if ever you see one of these on a flea market, car boot sale or whatever. You might pick one up and you won't be disappointed. Now, this particular instrument boasts 4 instruments, which is the frequency counter, what is a digital voltmeter, DVM, which is fully featured, and also a function generator and a 3-channel output power supply. So to look at the instrument as it stands at the moment, this is actually quite a a weird setup. I mean, you could visualize it as being a frequency count on top of a function generator. If you imagine it as all separates, you know, I can sort of see that in my mind's eye that somebody may have put one of these on the bench, you know, who designed this and thought, you know what, I've got a separate frequency counter, generator, power supply, and they sort of pushed them together on the bench. And the guy might have thought, or whoever it was that designed it might have thought, you know what, that'd be good in one box. So hence the reason why this was designed. But I have seen these before when I was younger, and certainly floating around some of the workshops and things, wanting to find work. I remember when I first left school, just before I left school actually, going around all the TV video repair shops in my area where I live, trying to find work as an electronics engineer when I left school, or as an apprentice. And I distinctly remember going around several of the repair centres around my area, which were all very busy at the time because there was a major market here in the UK back in the 1980s, where televisions and videos and camcorders, hi-fi systems were all being repaired, you see, to component level. And so therefore there was many businesses set up servicing those pieces of equipment to component level. And so naturally, the nice thing about it is that when you left school and you wanted to get into electronics engineering, and you were already doing it at home in your own time and learning, that you went around some of these businesses, knocking on doors quite literally and saying, making your own introduction, going in and basically saying, have you got a job, you know? And quite a lot of times, depending on, you know, what recession we were in at the time, because I remember the recessions of the 1980s and 1990s very well, it had a major effect on whether businesses were setting on anyone at all, whether it was fully qualified or even setting on an apprentice. So it was quite difficult back then to get into work, I do remember that. But that's how I found my first job, is knocking on doors and making personal introductions, going in, showing people what I could do, and meeting the engineers and the techs and the managers, and getting to know people, and then taking it from there. But yeah, I did remember seeing these on people's benches, or an earlier model of this anyway. Anyway, I've looked at some of the specs on these instruments online, and they did do a very nice looking version of this as well, which had more of a silvery black front on it as well, which must have been one of the models that came probably late on. But I still appreciate, you know, what thought went into this in the design concept of having all those instruments in one. And I think as well, one of the bigger purchasers of these instruments was a school system. I think they bought quite a few of these for schools as well. But yes, I have seen them in one or two places in my career. But obviously, depending on what industry you're in, will depend on what type of test equipment that industry will tend to buy. As you know, with the channel focus that my channel gives is mainly around radio frequency test gear, for measuring radio receivers and transmitters and amplifiers and filters, and you know, and designing radio circuits. So there tends to be a focus in those industry sectors into particular brands of test equipment, such as Marconi, IFR, Aeroflex, Hewlett-Packard, Agilent, Keysight, you know, Roden Schwartz, and you know, and everybody else that fits in between that. So you know, when you work in that industry, you tend to see only that equipment. Whereas obviously, if you work in television, video, hi-fi servicing, in yesteryear, even currently, you maybe would see combined instruments like this. So it's quite interesting from my perspective to see such an instrument, if you like, that's geared up for sort of the audio, hi-fi, TV sort of servicing area and education area. And I think something like this would be really good for a young person trying to get into electronics engineering, or digital electronics, analog electronics, or RF electronics, because when you look at what we've got on this instrument, which I'm going to go into shortly, you'll see that it does actually sort of stem into both arenas, whether it's RF or whether it's, you know, analog or digital electronics. And it's so useful is a piece of equipment like this to a student or young person, I think, that, you know, combines all the instruments in one. But as we can see with the design of the instrument, it is actually quite a big beast. I mean, it's not too far off the size of a Marconi 2955 radio test set with its width and what have you. But yes, it's all metal, it's well designed, it's very heavy. I'd say it's a good 20 kilograms, and it's certainly not something you want to drop on your foot when you're carrying it, because I think you'll certainly scream out in pain if it's landed on your feet. But if we flip it round just for a moment, it's well ventilated, there's no fan or anything, you know, whirling away in the background, so that's really good. The only fan you might be able to hear on the camera is the other radio test gear I've got switched on at the moment. But yeah, we've got a big beefy bad boy heatsink on the back there, probably for the power supply, which we'll look at shortly. We look like we've got some independent power switches as well for different instruments that's within the unit that you can switch on and off. In this case, it's the frequency counter and the function generator, so you can obviously disable those if you want. I can't think why, but obviously they put that functionality there. They haven't put a switch in for the power supply, or the other instrument obviously, which is the DVM. They haven't put a switch there for the DVM either, power supply or DVM. So you'd expect 4 switches, because obviously got 4 instruments independently. So I don't know why they've got a separate switch for the function generator and for the frequency counter, unless it's because if it's aimed at schools and things, they don't want kids playing with that or whatever, so the teacher can switch them off. I've no idea. Seems a bit strange to me, does that. The 9-volt battery there, which is quite odd, which you'll see when we review the digital voltmeter section, this is actually the power supply for the 9-volt battery. So it's as if I've taken the contents of a properly portable DVM and put it in the box, and then what they've done, they've kept the power for the DVM. It's probably for some isolation reason, maybe, for obviously the voltage that's rated on the DVM. It's perhaps to keep it from isolation from the rest of the instrument, so that it protects it in case there's a you know, somebody accidentally measures the EHT supply to a CRT tube at 20 kV and zaps the meter. At least it won't damage the rest of the instrument perhaps. But yeah, it's quite useful to know that if you get one of these instruments and the DVM doesn't seem to work, just replace the battery, because I think some people might mistake that battery as being for the memory backup maybe, or some other function, and not realise that it's actually the power for the digital voltmeter. And where the IEC mains plug is that comes in as well, we've got a connector which we can change the voltages. So again, useful for international markets where the power supplies are obviously you know, varying from 120, 100 volts, 220 and 240 volts. So that can go in different ways. And then we've got some fuses behind here, I believe, which protect the instrument. So I think there's several fuses in here which protect the instrument. So again, you know, another useful protection feature. With the heatsink on the back, I was expecting the instrument to give out quite a substantial current, which it does really. But what we'll do is we'll tear the instrument down a bit later and we'll have a look inside as well, and obviously reveal what's on this heatsink. But the power supply itself on this instrument is actually quite reasonably rated. It is actually, I'll just get something underneath it so that we can demo it a bit better. So on the power supply section, we do actually have a multi-channel output on the power supply. We've actually got a 2 amp output at the top, which I believe is the variable power supply. Oh no, that's a 5 volt output, fixed output at 2 amps. This here is the 15 volt output at 1 amp, and then the variable voltage 0 to 30 volts at 2 amps out the bottom output. And we've got obviously a voltage adjust, a current limit adjust. We can make the meter display either current or voltage, and we've also got a separate ground connection pod here. Got a light that illuminates on current limit, so obviously if we exceed the current limit that's set on that pot, this light will display. And the voltage obviously goes up to 30 volts, 0 to 30 volts. I think we've got a nice 10 turn pot. Yeah, it just keeps turning and turning and turning. So we've got that there. And then we've got the current limit adjust as well, so we can set the current limit as well, which we'll do a bit later. The power supply itself is switched on and off, or the unit power is switched on and off by that power button there. And so that switches the whole unit on. However, with regard to the digital voltmeter, which is this section, this has its own power button. So that's a bit strange, but there again it isn't in the context that we've just looked at, which is the 9 volt battery at the back supplies the power for this. And it does auto shut off as well, so if you left that powered on and obviously shut the workshop down so the rest of the instrument powers off, and then left it, this won't run the battery down, because after 5 minutes or whatever of no operation, it turns itself off anyway, until you next reset this button. But yeah, so on the DVM section here, we've actually got quite a bit. Obviously, you know, with the usual setup on most digital voltmeters, we've got a 20 amp port as well for measuring high current. We've got milliamps, a com, and obviously the volts ohms input as well from the leads. We've got a capacitor tester facility in there. I'm not sure what capacitance it can read up to, probably not a very high capacitance level. And then obviously we've got the usual features on the top there, which is the function, set, reset, DC, ohms, AC, continuity, up down ranges, and as well as that we've got these ranges here: logic, capacitance, diode, continuity in ohms, amps, AC and DC, milliamps, AC and DC, volts, and then millivolts as well. And when we look at the ratings, you know, 1000 volts DC, 750 volts AC, and then obviously we've got a fused current output as well, measurement capability, so at least we can protect it that way. And on the meter we've got what is a bar graph as well at the bottom, plus a current reading, and also then the main display as well. So we'll check that when we do this instrument testing. Now the frequency counter is quite interesting on this because it can serve two purposes. We have a frequency readout currently, which you can see on the display, even though we're not inputting anything in. But that's because when we look at the function generator, there's a little button down here which allows us to couple the output of the function generator onto the frequency counter. And so when we look at that, we've got this display button here next to the impedance selector, so we can select 50 ohm or 600 ohm outputs, but we can also couple the display of the frequency counter, so we can have it set to just frequency counter with that button out, or when it's in, it can couple the display then to the frequency generator, function generator rather. So when it's out at the moment, it will just be reading whatever is on the inputs here, but when we push it in, whatever frequency this is generating in the function generator section, then it will display on the frequency counter. And as we adjust the frequency on the oscillator, then it will obviously read it here, as you can see. So that gives us a readout, and obviously we're on to hertz now, so we're going down in frequency. So very good, you know, quite well thought out is that you're coupling internally the function generator's output to the frequency counter. And I think that yeah, so interesting. Now the frequency counter section has all the usual bells and whistles that a frequency counter would have. Multi-channel, obviously an attenuator is on this one as well. There's all the usual functions that you'd see with that. There's a gate, hold time, you can hold it, you can select different modes here, and inputs and comparisons of inputs and total. So you know, there's usual things that you find on a frequency counter. We've got to aid you reading the frequency as well, it will obviously display megahertz, kilohertz or hertz, so then when you're looking at the frequency you're not going to make a mistake in, is it, you know, 7 megahertz, is it 7 kilohertz, that kind of thing. So at least it gives you that indication. On the channel input, it's a little bit confusing because it says on the display channel A, B, C, but yet the ports don't go A, B, C. They actually go A, C, B, which is odd. I don't know why that was. You'd think they'd be the other way around, wouldn't you? You know, they'd turn them that way around, so it's A, B, C. So, but if you have a look here at input C, it's actually quite fully featured when you think about it, because this is a 1.3 gigahertz frequency counter. So that's very useful, in particular for measuring transmitters Obviously not directly in, you wouldn't put 25 watts from a PMR radio or an amateur radio set into that socket, which would obviously cause damage. But yeah, through a sniffer or a coupler or an antenna stuck to the front and then a handheld radio keyed up nearby, it'd certainly read the frequency. But what I've noticed as well is down here is the actual warning is set to 250 volts peak to peak on the input. So that's a hell of a voltage in comparison to most frequency counters. There aren't many frequency counters I can think of, even separates, that can give that kind of protection on the input or rating on the input. So yeah, quite interesting. But as far as RF power is concerned, obviously, in my mind's eye, 25 watts into a 50 ohm load, whatever that would equal peak to peak in the sine, in the sinusoidal wave of the frequency, whether that would get anywhere near 250 volts AC. So theoretically, from a voltage perspective, if you're a theorist and you worked out what the sinusoidal wave peak would be at RF at 25 watts into 50 ohms in voltage, if that was under 250 volts and you worked it out to be that mathematically, one would think that you could connect an input into there directly and obviously use a transmitter into it. But as experienced RF engineers know, that wouldn't work, simply because of the fact that the impedances are different. This is up to a 1 meg ohm input, so yes, it will cause damage. So yeah, you have to be a bit careful with that, especially those that are new into the game, where we're trying to work things out from mathematics, not realising the impedances as well of the input are not 50 ohms. So yeah, you have to be careful with that. As long as you loosely couple RF in to the ports to measure the frequencies, or low level RF from signal generators or low energy sources, then you're fine. But it's certainly not recommended to couple a transmitter directly into these ports for obvious reasons. Okay, so what we'll do some tests now with the voltmeter, power supply and the function generator in putting a frequency into the frequency counter from an external signal source, trying to read the frequency accuracy. The function generator will give some outputs out of here and measure what these potentiometers do and how you can set them. The output of the voltage of the power supply, we'll have a look at that in the DVM, some of the functions on that, and then we'll strip it down and have a look inside. Okay, back soon. Okay, so on the function generator section, we've got the output coupled to our oscilloscope test instrument at the moment, so we can have a look at the output characteristics. Now, we've got on the function, we've got sine wave, square wave and triangular wave. So obviously if I push these buttons in, we can see the waveform change, etc. We've got on the BNC inputs here, we've got VCF in, so I think there's a function there to allow a signal to be coupled in. We've got the TTL, obviously a square wave output, and then obviously the main output. Those impedance can be selected between 50 ohms and 600 ohms respectively. Likewise here we've got an amplifier section, offset, SYM or symbol. We've got sweep, width and rate, and they have dual functions to these pots because they pull out. So if you pull it out, it gives a minus 20 dB attenuation, and likewise we can see that here on the display. So if I turn it down there, that pot to the left, and then turn it fully up, then we can adjust the we can adjust the output level, and then when you push it back in, obviously the level comes back, and then we can increase or decrease accordingly. This is a frequency control, and it's obviously being read here at the frequency that we're giving out. for it, you have to then go to the next range, and then, you know, so and then obviously we've got the offset as well, where you can pull that, and then we can adjust it one way where the negative side of the wave is being offset, the other way the positive half's being offset. So that's that potentiometer. The symbol, pull that to adjust it. And then we've got sweep rates as well, so we'll pull that. All sorts of little adjustments that you can make onto there. Down here on the frequency side, we've obviously got, you know, times 1, times 10, times 100, and times 1000, 10k, 100,000, 1 meg. So it is actually, have a look at the frequency accuracy against what the frequency counter reads. It says that the, let's change the filter. Okay, so the frequency is on the frequency counter is reading 603 hertz there, or 603.2 hertz to be accurate. Let's see if I can get it to focus properly. There we are. And then if I come down to here, we've got 603.2 hertz. So it's very accurate. So that's reading 1002 hertz, or 12 hertz, it's different between that. So let's see what it says again, you know. So it's very accurate. So not only is that part of the instrument accurate, that the frequency counter is accurate as well, showing you the output of the signal generator, the function generator being coupled into the signal input of the frequency counter. Now I think this goes up to about 2 megahertz or something like that, which we'll have a look at on the RF spectrum next, and let's see how high a frequency this goes up to. Okay, we've coupled the output again of the frequency generator output to the frequency counter by pressing in this button. We've selected the maximum switchable range and frequency, and the knob won't go any further up in frequency. So maximum capability frequency generator wise is 2.1 megahertz. So yeah, that's the maximum capability of that. Would it be nice if it had had, for example, AM and FM capability and up to 30 megahertz? Then it could have made a nice test station for HF, or even if it had had a you know, an HF signal generator in it, up to say 50-60 megs, whatever, it would have been able to be marketable. This in quite a lot of other markets that it currently can't reach, which is obviously dealing with radio transmissions and reception directly. But still, it's still good, you know, can't grumble. Nothing wrong with that. Depends what you want to do, obviously. Over to the digital voltmeter section and power supply now. I've set up a measurement where we're reading the output of the variable output power supply. So as we adjust this, we're measuring that into here. So we've set it up at the moment for 19 volts DC output. The meter says we're doing 19.26. If I adjust the voltmeter or the voltage output coming from these two ports, we're up to 20.6. That says we're doing 20.9, so its accuracy is well within its tolerance, its output, the tolerance of the power supply, so that's okay. We've got a voltage and an amp section here which will measure the current limit shortly. On the voltmeter side of things, obviously we've got capacitance, you know, all the different current functions, diode, logic, the lot. So that's all in there, as you're probably aware of with most voltmeters. That capability is there. Haven't seen any capability for HFE for calculating the gain of transistors, so that's not on this. So it's a sort of a middle of the road, you know, meter. These days in particular, most meters come with HFE, capacitance and all the other features. But there again, when we look back at when these were made, you know, obviously 20-30 years ago, that wasn't a common thing found on many meters. Capacitance certainly. So, you know, if we step back in time to when this was actually manufactured, this was quite a high spec meter with regard to what it can do. So, you know, we mustn't forget that. But in comparison to modern day standards, obviously this is a fairly low middle range sort of DVM meter. Now if we just move the put this to current DC amps, so we want to measure DC amps, but before we do that we'll just remove the lead. Obviously you never put voltage in from a power supply if you're going to read ohms, for example, or do. Most meters have got some kind of protection built in, but a lot of the older meters don't, and you can blow the meters quite easily by going to the ohm setting there while you're feeding volts in. So that's something to be aware of, and it's just decency to do that anyway, obviously, because you don't want to damage anything. So yeah, be careful with that. We can go to amps. I'll wind the current limit to minimum. We'll then go to the 20 amp scale, obviously, which we're reading now. And if I just adjust the current, if I can get that out of the way, so let's get it up to something like an amp. That's 2 amps already. Let's have a look. Current, that's it. I was on the wrong range. Then adjust it to give an output. Oh, the probes have dropped out. This is what happens when you try and do a measurement. You see, you disturb something and then the probes drop out, don't they? So I'll put the negative one back in there, just rest it in there. It'll do, but just for this measurement. And then we'll adjust the current. There we are. So we've got the current limit light on, obviously. You know, so that's like try and get 500 milliamps out of it. We're nearly there. 510 milliamps. It says we're doing 506, so it's fairly accurate. We can't grumble. You know, if we get it up to an amp, let's have a look here. That's an amp. So again, the differences between them barely noticeable. And then if we get it up to like 2 amps, well, let's try 1.5 amps. 1.480 amps, it says on the thing. If we get it right up to 2 amps, 1.967. Maximum current it'll go up to is 2.1 amps. So yeah, very good. And It's surprising, really. Obviously we've got separate outputs here, 15 volts and 5 volts. So I'll move this back to what is the DVM, the voltmeter side of things, and we'll select voltage, and we'll just check the outputs on those. Let's have a look. Now I think the supplies are isolated, though I'm not sure. We'll just have to check for that. So if I go to the earth there, yes, they are. They're isolated. So I have to go to the ground there. 15 volts, yeah. And likewise on this port here, if I can just get my fingers out of the way, there we go. And that's 5 volts. So with 5, 15, then a variable supply as well. So quite a nice little instrument. Now I've got, where is it? Did have an electrolytic capacitor. It was quite a high value electrolytic capacitor that I tried putting in here, and it wouldn't read it. It was just over the limit that it could go to. And that's the annoying thing about digital voltmeters. A lot of them, even the high-end fluke meters as well, like the fluke scope meter that I have, it does have the issue of only reading up to a certain capacitance level. So if you're reading electrolytics that are typically in power supplies, you know, at 10,000 microfarads or above, it won't physically read that, which is a shame. And that's the thing that I found with the fluke scope meter as well, that it generally won't read capacitances over, I think it's 5,000 microfarad or something. So, you know, again, it's got limited capability. And that's the thing that I've noticed with a lot of these multimeters as well that measure capacitance, is that they generally can only read up to a certain relatively low capacitance level, which, as we all know, when we're repairing power supplies, the electrolytic smoothing capacitors in power supplies, for example, are actually quite high value in capacitance, and so a lot of these meters won't read the capacitance levels because they're too high. So you need a dedicated ESR or capacitance meter separately for that. But yeah, we'll put some components in now and read that as well, and resistors, capacitors, diodes, etc. Okay, so we've got a selection of various little components here floating about. We've got some silicon transistors, germanium transistors. This is a Mullard OC22, I think it is, or OC25 or whatever. That's a germanium transistor. This is a germanium diode, which I think is an A71 or something, like a cat's whiskers diode. We've got an electrolytic capacitor, polarized. We've got a resistor, another diode there, silicon diode, and another silicon diode. We've got a non-polarized capacitor as well, and another electrolytic here, but this is quite a high value, so we'll see if it reads that. Okay, so if I just, this is a 1N, I think, at whatever the voltage that is rated at. Let's have a look at its rating, see if we can get it focused. So that's 1 microfarad at 100 volts DC, that's rated at. Okay, so let's see how accurate that is then when we push that in there. Obviously on the front here we do have a polarized input for electrolytics, so you just have to, you know, make sure that you're aware. You have to push the leads in quite a way before it makes contact. It's only just making contact now with the things, the receptacles that you push it into. So we're getting 0.879 of a farad there, so of a microfarad, so it's nearly 1 microfarad. It's within its tolerance, quoted on the front, how many percentage it is, so that's gives us an idea of that. It also says on the display as well, if you missed it, just down there it says microfarad UF there, and then obviously it puts a marker as well near where it is, so we're not far off a 1 mic value there. Okay, so let's try, for example, another capacitor. So this capacitor, I believe, is I think that says it's again a 1 mic, I think. Let's have a look. Is it a 1 microfarad? I think it is, isn't it? Let's have a look. Oh, it's a 10 microfarad at 25 volts. And this one obviously is polarized. So we need to get this the right way around. So that's the positive end. Obviously, if you're testing capacitors out of circuit, you're taking them out of a power supply, for example, or a circuit to test them. Always make sure they're discharged before you put them in the tester, because otherwise it'll blow the tester up. So let's just hold that there. So again, that's reading 0.9, so 0.9, 9 microfarad, 9.39 microfarad on the display, so it's almost 10 microfarad. And so it's fairly accurate with the capacitance side of things. So let's measure some germanium diodes now, and transistors. So if we put that to the ohms, we'll measure a silicon diode first, actually, just for a comparison. So if I connect that up on the meter, let's see what happens. It's always difficult working one-handed. It's almost impossible at times, especially with these probes, because the ends of the probes have been used that much now. They're all getting sort of worn out. I'll have to buy some more. Okay, so that's the I'll put it on diode. It does help when you got it on the right range, doesn't it? So the junction on that, I'll read that there. It's 908 millivolts. That's quite high, actually. I would have expected it to be around about 700 millivolts, but I suppose it depends on resistance of the probes, etc. So that's a silicon diode. The next one is this. I think it's an A70 Germanium Dial. These are extremely old diodes. They're basically cat's whisker diodes, and they're very expensive as well these days. They're made by a company called Mullard, which has long since gone now. But the OA90 series, OA70s, OA60s. So this, obviously, germaniums and silicons have a different forward conduction value. So this is basically nearly 200 millivolts, or 192 millivolts, as can be seen there. And so basically, germanium diodes were used a lot in RF applications and classic radios and things like that. And likewise, the germanium transistors as well were very popular, particularly around the 70s and 80s, late 60s, early 70s, etc. They were very well used, and there still are very sought after transistors, germaniums. There are certain types which I've got, which are used in things like guitar amplifiers, etc. And so we've got various germanium types of transistors in this little box that I've got, and matched pairs as well, you know, AC 128s, 153s, one whatever, different types of transistors. This is a, what is this? This is an AC 187-01 and an AC 18, is that 188? So they're a matched pair, push-pull type pair. And again, these were used a lot in guitar amplifier pedals, and obviously they're still very collectible even to this day. Audio amplifiers, signal amplifiers, etc. They were all used by you know, by various equipment manufacturers. So there's a big following in germanium devices even now. simply because of, you know, people restoring old classic guitar amplifiers and audio amplifiers from, you know, the 1970s, 80s, etc., and even a bit before then, 60s, that often employed these devices in them. And the way that you could tell on like the Germanium diodes what their part number was, because as you can see there is no part number whatsoever on that. You can actually just see inside, if the light's not in the way, there's actually the little cat's whisker inside. You can just see it in the bead there, that little wire that's going to the what is the germanium wafer, which I think is at the bottom there. See if I can get it to focus a bit better. But that's the germanium wafer and the little whisker, and depending where that whisker is on the germanium wafer depend on how it operates. And the way that the part numbers are worked out on them is the coloured bands. There were all the OA range part numbers that were Mullard made, and then they would put coloured paint on, and that would follow the same as a resistor colour code. So it would naturally then tell you what the part number was on the device by using the coloured band to tell you how that part number worked out, and so you would know what type of OA diode it was. And yeah, so again, same with the transistor. I've seen some of these as well where they've actually got emitter and base markings on them. I think this might be a PNP actually, or an MPN, I'm not sure. I think these are PNPs, these OC, this particular one. So again, that's across the base emitter junction on the transistor. So we've got a forward voltage there of 135 millivolts. So that, you know, obviously is that forward conduction voltage. Now likewise on a silicon transistor, this is a TIP3055. There was a transistor in that package, what's called a TO3 package, that was a 2N3055, which is used a lot on DC power supplies, particularly high current DC power supplies. They also made it in that package style as well. Can't handle as much current as a TO3 package can, but again, I think it goes base collector emitter. So if we make the base positive, because this is an NPN transistor, and then this probe, it's not playing ball today, is this one? Let's see if we can couple onto it. There. It keeps twisting round. I'll have to get rid of it. It's melted slightly at the end, which is then causing it to stick. So sod it. What we'll do, we'll go straight on the pinner cells then. There we are. So that obviously has a higher conduction point of nearly 0.6 volts there on that base emitter junction. So that's the difference between silicon transistors and germanium diodes and transistors, is a forward conduction properties as well. It's a main significant difference. Obviously germanium components as well of there are other things that we'll go into later in another video, but they have leakages, and you have to test them for gain, HFE, that kind of thing when you use them because of the germanium construction. And so that's that, a silicon and a germanium transistor and a diode. We've looked at the silicon diode already. The capacitor, that's another type of diode, which is found in many rectifier circuits, etc. We've got a resistor here, as well, which I think if we look at the colour code, I think that's I think it's a 1K, that. Yeah, definitely a 1K. Yeah. So what we'll do, we'll just quickly measure that, if we can get on it, because it's again tiny, minute. We'll put that to ohms, obviously, and then we'll measure that diode, that resistor rather. So again, that's nearly a 1K resistor. It says there in the display K ohm in the bottom right hand corner, 0.99 K ohm. So yeah, for a nice little instrument. If you're interested in getting one of these, at least you've seen its capability and what it can do. You know, it's obviously quite a fully featured little unit. So yeah, next thing we'll do, I think, is strip it down and have a look inside and see what it's like inside. So I'll be back to you shortly. Right, we're back. I just wanted to have a quick demo of a germanium component, being this germanium diode. You can just about see there on this zoom level that there's a little sort of cat's whisker that's pointing down onto that wafer, and the germanium wafer, which is at the bottom there, actually has a sweet spot on it. And if I magnify it slightly, I'm trying to get it to zoom in, you can just about see that it's pointing right on the edge, on the corner of that wafer. And basically that little sweet spot is tunable on these. The difficulties of manufacturing these were extremely difficult back in the 1960s, 70s, etc., and trying to get that wire to bond, that gold wire. And what they often used to do, I'm told by people that worked at the factories that made these, is they would it was potluck really in a lot of ways. They had a lot of failed devices when manufacturing these types of diodes and transistors, because obviously transistors are manufactured in the same way with regards to you know, where the cat's whisker touches on the wafer. But basically they used to make them, and that's why they didn't have the part numbers on them until after manufacture, because when they tested them, depending on what specification the diode was when it was tested, which was entirely denoted by where that cat's whisker touched on that piece of wafer, the germanium wafer in the bottom there, that would denote the naturally the characteristics. So they were all very slightly different, and so they made a range of diodes in different tolerances, different specs, and they would test them, and depending on where the diode fell in with regards to spec, then that would put it into a certain part number category, and then they would put coloured paint, as you can see there on the ends, to not just signify the anode and cathode end, but they would also put coloured bands on the end, and that would tell the person purchasing the device what the part number was. And so yes, that's a gold bonded wire that goes to the germanium wafer, which is on the end of that electrode. Now, the manufacturer of these devices, the OA series, was mainly a company called Mullard, and the good old days when you used to have catalogues for electronic components, and basically Mullard produced a series of books, which I've got a collection of. But yeah, this is 1971-72 is this book, and then within it are the Germanium Diode bonded, gold bonded series. And so basically you had the OA47 general purpose high speed switching. Again, you had as well the germanium point contact diodes as well. So there's a gold bonded diodes, and then there was a point contact diodes. And so you got the OA90 series. OA90, OA91 diodes are still used commonly as well, and they were the specs there for those diodes. But depending on, with a lot of these diodes, where they fell, it would all depend on silicon whiskerless diodes. Yeah, so depending on where the specification of that diode would be when it was, you know, under test, would categorize it into what part number range it would fall into. And so they would then put on the glass bead of the diode obviously a colour code which was exactly the same numerical value as the resistor colour code is. So you could work out it would be an OA61, you know, or an OA71 or whatever, depending on what the colour was, the last two colours. And so we've got different package styles and things like that as well. But a lot of these classic components were done very differently. I think it tells you that here as well. It says that, for example, on this diode, it says, when it focuses, if it focuses, coloured band and when used in rectifying circuit, and positive, so they give it a coloured band or and positive end. Yeah, so that's what they did with a lot of these. They put like a coloured paint dot on the end there, a couple of different paint dots, etc. on those type of devices. So there's all sorts of little things, you know, but again it's interesting because of the fact that if you've got the data books, etc., and you can find out, you know, quite a bit about these transistors and diodes and how they were marked up. So yeah, quite interesting. But I just wanted to show you inside that, because it's very rare these days that you can see inside any device, let alone a germanium device. But that's apparently what they did at the factory. You know, they would assign that part number depending on the spec and how it worked. You can just see though, you know, it's only tiny, that little gold wire, and that's why you got to be careful with them that you don't bang them. And they often did suffer with microphony, where vibration within the device, physically vibrating, would have effects on it. And it's said that germanium transistors, when used in power amplifiers and audio signal amplifiers in particular, and it's probably the reason why guitarists favour them, and there's still pedals made to this day with the old transistors in them, because the musicians swear by the audio differences of quality. It's a bit like the difference between valves and solid state transistors, you know. People do say that it's a better sounding property using these devices, and so often you'll see even modern guitar pedals that have got the OA germanium transistors and diodes, and the OCs, the ACs. I think the AC 128 transistors are very popular in guitar instruments. So yeah, very, very interesting. But there's all kinds of different devices in the germanium range that are still used to this day in all manner of you know, very niche areas of the electronics market. So yeah, anyway, I'm glad that I've shown you that cat's whisker thing in the on the wafer. But it's interesting how these things were manufactured years ago, and and I think as well, you know, the general following of germanium devices is quite high these days. And they come in various package styles as well. There's quite a bit of variance and differences between them, you know. That's an old transistor, that's probably a silicon one, that, but you've got, you know, these very old transistors, a lot of these. I have a lot more of these as well, got quite a significant quantity, but again, you know, I keep them because they're the classic devices, and occasionally when I get audio gear in for repair, amplifiers and instruments and things that I often look at for people, these transistors are often found within, so it's always worth keeping things like this. I've got the A70 series transistor diodes as well, A90 ones that are used in RF probes and things, but quite an interesting little device. So look forward to seeing the next video. I'm just going to go and strip this down so we can have a look inside, and that will be in the next part of the video, so bear with me, we'll be back soon. Okay, so this is what's inside the instrument when we've got the lid off. So as we can see, we've got the usual sort of configuration, big hefty transformer. I'll just flip it up so that we can see it a bit better, and get some additional lighting, I think. Yeah, so we've got the usual configuration. Notice two transformers in it, this transformer and that one. Obviously this transformer, from the size of it, I would assume provides the separate DC rails that are coming out the front. If you remember, on the front we've got the a post on the front for the three different supplies, the 5 volt, the 15, and also the variable 0 to 30 volts. So this is a power supply board, and all the regulation and regulators. These are the connectors that go off to the front panel, and these are obviously the, you know, the series pass regulators, smoothing caps, and we've got a bridge rectifier as well down there, which is this device, and we've also got some bridge rectifiers there for the isolated supplies, and more regulation. So obviously this power supply board also doubles up as a power supply for the rest of the instrument as well. I think the separate transformer is probably for powering the unit itself, rather than having it off the same supply as the output power supply is. So as big as that heatsink is on the back, which was fairly enormous if you remember at the beginning of the video, we've only got some sort of small sized transistors down here, which will probably be the series pass regulators and the voltage regulators. So they're you know, obviously bolted to the heatsink on the back, which doesn't get terribly hot. That's a frequency counter board here, with its reference crystal. So if you did get one of these and it was off frequency a lot, chances are this has drifted off frequency, the temperature controlled crystal oscillator, which is here, and that's running at 10 megahertz, and you can adjust the frequency accuracy with that potentiometer. So if you feed in a known signal source in through the front onto the frequency counter input sockets, these, and there was off frequency by some way, you could calibrate the instrument by adjusting that, and then all the frequency componentries under these cans for the 3 channels. So there's not much to see on the frequency counter board, I'm afraid, and so that's just the power supply section on the top, and the frequency counter board there on the top as well. So we'll turn it round. Everything's well, mains filter down there, well insulated, and we've got the fuses as well, the fuse section. underneath we have the board, which is for the function generator board here, and the calibration pots to adjust it all, etc. The multimeter section, which is actually on the top, along with the we've got a frequency counter, the function generator side this side, frequency counter on the other side that we've seen. This is the power supply section down here, and then of course the multimeter is actually inbuilt on the back of this, so it's actually on the back of there, behind this plastic cover. But we've got a PCB behind there that's bolted on the front, and that's for the multimeter. And then obviously the power supply, voltage display, current meter, etc. is on this PCB at the bottom there, which feeds, takes a sample of the voltage from the output ports and measures that, which is this section at the bottom. So yeah, it's quite a nice little device. So yeah, I think there's another board under. If I remember rightly, last time I had one of these apart, there's another board under here. You take this board out and then it displays another board, which I also think is something to do with the function generator as well. It has all the boards, the board on it for the potentiometers here that pull out. So this board is where all those switches are located there, and then when you take this board out, the other board with some more circuitry on it is for those potentiometers there. So that's a little rundown of the device. What I'm going to do while I've got it apart, because these sometimes don't latch properly and stick in and they pop back out, I'm just going to lubricate these switches with some switch cleaner, spray switch cleaner, and I'm just going to get that in now and some out of those switches and just lubricate them all so that they all switch nicely. So yes, I hope you've enjoyed the video anyway. I know we've gone off piste a little bit with looking at obviously the the germanium diodes and transistors and things, but at least you've seen the capabilities of the unit and what it can do. And the nice thing about it is that it's a 1 in 100 sort of example that I've got here in the workshop, that I can generally show some general electronics test and measurement as opposed to RF gear. So it's nice for me to just diversify a little bit into a slightly different area to what we normally focus on this channel, and also see some of the capabilities of measuring components in the real world and what it can do. So if you see one of these, I think they're worth getting, definitely, especially with the 1.3 GHz frequency counter as well, and power supply and voltmeter. It's all worth having. So thank you very much for joining me today for this video. Keep tuned for some more test gear related videos, repair videos, demo videos, and we'll see you in the next one. Thank you for watching.